Right, so I don't know if I've got much time to go through this, but I'll attempt to go through it anyway. Well, I've got that up there. There you go. I always say get the book, get the book. Um, the Zen of Python. But no, we're actually going to go through this, which is the Euler method. I'm going to attempt to go through this. Something that was done at university quite a while ago. So yeah, we'll just see how it goes basically. Let's see. I'll open up my VS Code if I haven't got it open already, which I haven't. And I guess I don't know where it's going to open to actually. It's open to daily questions. I wonder if there's any syncing to do because I did in the daily questions section. Just wonder actually where I put that little piece of code. That's a downloads folder. I put it stuck in the C drive actually. C Python daily questions. So let's just go to. In fact, I don't even need to do it there. I can just go to revealing file explorer and go to the level above, which is here basically. Go to the level above, and yeah, I had that little image in there, so it's the right folder, I think. So anyway, I'm gonna close this one. Alien dig.py. I'll close this because that was for something else, pyramid and stuff. Right. So let's just go back. It's what is the Euler method basically? Let's zoom in a little bit. And there is an implementation down at the bottom. And this book is called Python Numerical Methods. I mean, all of these numerical methods they apply to all programming languages. It's quite a cool sort of thing. You know, the code's down here somewhere, so we're going to maybe try and implement the code in VS Code. And I guess there's some illustration or some answer or something that we're going to get out of it. I see there's a matrix operation down at the bottom too. So yeah, let's have a little read. But the Euler method, let ds by dt equal some function of time and s of t. So ds of t. So there's this, there is a function of s, and we're going to find there's a function s of t, and we're going to find the rate of change of this function with respect to time, basically. And it can be explicitly defined as a first order differential equation where f is the function, is a function that returns a derivative or change of state given a time and state value. Also, let t be the numerical grid on the interval t0 to tf. So it starts at t0 and ends at tf. Wonder if I've got my little thing open. I don't, which is over there somewhere. I should just open that just because it's easier to highlight on this thing. So yeah, we start at t0. I mean, there is an image down there. That's the worst zero ever. Let's hit the undo button there. We start at t0 and we go all the way up to some final time, which is tf. That's kind of like what that piece means. Again, that's the world's worst f. It looks a bit more like an e, but it doesn't matter. Get rid of all of that. And yeah, which is this piece here. Well, here tj and tj plus 1 on the steps. So it's the first piece on the t line and the last piece on the t line, basically. The timeline, t standing for time usually, with spacing h. Okay, without loss of generality, we assume that t0 equals 0 and that tf equals nh for some positive integer n. So it's just some equal spaces basically, and the distance between all of the gaps, I guess, is h. So there's lots of little h's. And here's, I guess this is one step. So I won't leap forwards. We'll just see the setup as it's built. The linear approximation of st around t at around tj at tj plus 1 is, so an S is here representing, I guess, a position. That's the usual thing, but it could represent something else. So S represents a bit. So the S at this new time, at this time incremented like 1 second later or 1 unit later, whatever that is equal to the position at the starting point, and multiplied by this distance, this tj plus 1 minus tj, which is actually h, because we're told that you've got an h steps here, so not the n but the h up here, and then multiplied by the rate of change of ds by dt. So how fast does it change? And it can be written like this. So we can see that this piece here basically reduces to h, and this piece here, I guess, is a derivative, is at ds by dt. So we generate some function that's based on time and position, and that's pretty much it. So the formula called the explicit Euler formula, after Leonhard Euler, because he's always in all maths things pretty much. Formula called the explicit Euler formula. This formula is called the explicit Euler formula and allows us to compute an approximation of Sj plus 1 given the state of Sj. Starting from an initial interval value of S0, and S0 is set to the value of S at time t equals 0. That's what this little subscript means. It means S at time t equals 0. So we can use this formula to integrate the states up to S of t of f, which is basically S of t. These S of t values are then an approximation for the solution of the differential equation. The explicit Euler formula is the simplest and most intuitive method for solving initial value problems. At any state, t, S of tj, it uses f and state at a state to point towards the next state. So it's going to use, basically, it's going to use this slope, and this slope here is, I'm going to draw in green here, I guess. It's that base that it's referred to. He's going to use this slope to get some kind of approximation going from here and ending up over here. And we can see that, like, it's not an exact approximation, like, because you've got this little gap over here, but it's that's what it is. There's loads of other methods. This is one method, but using the slope is quite good. It arrives at the solution quite fast and quite stably under many conditions. So, although there are more sophisticated and accurate methods, oh, there you go. So it's going to say, although there are more sophisticated and accurate methods for solving the problems, they all have the same fundamental structure. So there's like Newton-Raphson and other things like that, or you could even kind of, like, I don't know, assume a value like at a much greater point and like get that and double it and find the average and so forth. As such, we enumerate explicitly the steps for solving an initial value problem using the explicit Euler formula. And what's going to happen here? Assuming we're given a function of s, assuming that we are given a function, so it's this derivative function f of t of s of t, that computes the rate of change of t of s of t with respect to time, which is this dst by dt, a numerical grid t of interval t0 to tf, an initial state. We can compute the s of tj, so we can iterate through this thing and get each consecutive element for every tj using the following steps. We store s of 0 into an array, and then we compute the next step, which is basically the previous step plus its distance multiplied by the slope, this derivative over here, and then we store that, and which is its new value. Basically, the only difference between this one and the above one is that it is t1, so it's s1, which is s of t1, and then we compute the next one to get s2 and so forth. And again, s at time t equals 2 is s at time t equals 1 multiplied by this constant, the gap, because we just split it into equal portions of time, multiplied by the slope, and that's pretty much it. So yeah, and then and so forth, and we can keep doing this indefinitely. So s at time f, we can just keep computing that from the previous ones basically. S is an approximation of the solution of the initial value problem. When using a method with this structure, we say the method integrates the solution of the ordinary differential equation, and we're going to try it. The differential equation f of t equals e to the minus t, df of dt equals e to the minus t, with a initial condition of f0 equals -1, has the exact solution. So I guess, what is that here? This piece here, this df by dt, which is equal to e to the minus t. The usual differential bit is you take the negative. Like my differentiations, ages, but you just stick a minus in front of that. This is quite a good function because e to the minus t shows e to the x, the differential of e to the x. So d by dx of e to the x conveniently comes out to be e to the x, and that's because this is positive, and if there was a negative here, it would actually be that. So it's kind of like a convenient function for all of that. So yeah, what we're going to do, we're going to use NumPy. NumPy is very common. We're going to import matplotlib.pyplot as a PLT. That's for the purpose of charting. It's got some striles here. I'm not going to do this. I wonder if I could use a Seaborn thing, but I'm not going to do this inline thing because I'm not going to do it in a Jupyter notebook, although I could. So I'm just going to go, I'm going to do all of this, so copy, and I'll have to go in here, and I've literally only got about 7 minutes, so, oh, I've got to install an update, do I? Install update now. I think I've done all of the updates. Preparing. I wonder if I should have done that a little bit, because I'm going to run out of time. Closing applications. Come on then, do your job. I'm just going to address that I'm putting on the system now, because it doesn't seem to be, sort of appears to be hanging, which isn't. I'm just looking here, the CPU isn't even running, so that might require a refresh in that case. Just close that out. Oh no, it's going. There we go. Right, so we're going, because I think I did this update before, but anyway, just do it again. You get these updates like once every month or something, or once every few, whenever they do an update. But yeah, I quite like the updates, and I like the updates in Chrome as well. It keeps everything really up to date, basically. So I get two things that are opened here. That was my test class method. That's in general test. Let me just close that one down. This is the daily questions. I just wonder what I should be opening here actually. So let me just go back here. I've got different options. I might go to the, I don't know if it, I will go into the daily questions. Don't know why. I have to put it somewhere. Brilliant.org. And I've got a math section, so what I'll do is I will go in here and I'll put what were we actually calling this here? I will go and call it the Euler method, explicit Euler formula. So let's go back, new file, explicit underscore Euler .py, and I wonder if I've got the paste straight in there. I do. Now this piece is not going to work, so / that out. Right, and I'm in the virtual environment, so I'm going to have to do, I'm going to have to pip install NumPy in this VE virtual environment. because it's not recognised. So here, click install NumPy. Ooh. Surprising that NumPy doesn't work in the virtual environment there. It's an interesting one. And installing the packages. Interesting. Okay. Right. I'm just going to do pip matplotlib just to get the matplotlib, the original docs. Yeah, it's just that. Okay, fine. I've already got that zoomed in. I'll keep that on there just for the sake of it. I don't know why. Let's just go back to the explicit Euler and just paste that in here and then do that. Right. So this piece of code, which is an old piece of code, let's just, this piece of code here, which is an old piece of code, the linter doesn't like that. And why not set it on 2 lines? Is that what the linter's like complaining about? Let's have a look. So over here, do not assign lambda expression, use a def. Okay, that really suits me actually. I wonder if quick fix. Oh, that's beautiful. Look at that. I've got my own opinions on that, but I'm not a fan of lambda functions, so I'm actually glad it's done it anyway. Yeah, it looks like we're good to go. We've got a plot.show, so let's just see what happens here. I'm just going to do an F5 to run everything. Let's see what happens. It's either going to pass or fail, and I've got to go in like 2 minutes. So an error has got, okay, but that's because it's no longer a valid package style. Okay, that's an easy one to get rid of. Boom, don't want it. I had a feeling, well, I don't know, but anyway, yeah, that's gone. So we'll try and run that again. By the way, that's the thing about Python being interpreted. And there we go, we've actually got the answer. I'm going to have to continue this video, not the answer, but like we've got the code working. I've going to have to come back to this video. Quite like that. These are the exact solutions. That's the approximation. We can see that they're relatively close, but I haven't done it. I haven't investigated everything at this point. But we have got it working, which is quite nice. I'm going to go over here and I'm going to right click here and implement explicit Euler method for solving ordinary differential equation with a visualization commit. That's our commit to Git, save the changes, and I guess that's going to be it for now. I'm going to have to do a follow-up because it's quite nice. So that's our explicit Euler with the approximate and exact solution. And yeah, if you do like everything, follow, like, subscribe, all the rest of it. I want to get a bit more done. I see there's more stuff underneath here actually. In above, we see that each dot is one approximation based on the previous dot in linear fashion from the initial value. We can eventually get an approximate solution. We get a better approximation for the solution. So here already we get some kind of, there's some discussion and get a better one. I want to go through this. That'll be the next video. If you've got any comments, by all means put the comments in the comments section or whatever. That'll be interesting to see what people have to say regarding the comments. And I'll put a hello message in the comments. And yeah, like, follow, subscribe, get the book. Yeah, that's a Python website. So it's a good local Python website. And yeah, that's it. The Euler method. Euler method, the explicit Euler formula in Python, very quickly, and we'll do a little bit more at a later stage.